Good morning and welcome to our Alaska Collaborative on Health and the Environment teleconference with Dr. Molly Kile about the new study on exposure to flame-retardant chemicals and social behavioral outcomes in early childhood. My name is Diana DeFazio, and on behalf of Alaska Community Action on Toxics, I'll be facilitating today's call. CHE Alaska is a regional partnership group of the National Collaborative on Health and the Environment. CHE Alaska aims to advance knowledge and effective action to address growing concerns about the links between human health and environmental factors. You can find more information at akaction.org and healthandenvironment.org. And again, for those who might just be joining us, everyone who signed up for the call should have received a link to Dr. Kile's presentation this morning. And if you did not, please send me an email at Diana, that's with one N, at akaction.org, and I'll send it to you after I introduce our speaker. As with all of our CHE Alaska teleconferences, we'll leave time at the end for discussion and your questions. Now it is my pleasure to welcome and introduce our presenter for today. Dr. Molly Kile is Associate Professor in the College of Public Health and Human Sciences at Oregon State University and Principal Investigator of the study she will be discussing today. Her major research interests are environmental, molecular epidemiology, and global health. She works to understand how exposure to chemicals in our environment influences maternal and child health, and more specifically, how chemical exposures in utero may alter epigenetic mechanisms that could contribute to chronic diseases later in life. She is also interested in how genetic and other individual factors, such as nutritional factors, may interact with chemical exposures to influence susceptibility to disease. She has a strong background in exposure biology and developing cohorts for environmental epidemiological studies. Dr. Kile received her doctorate in environmental health from Harvard School of Public Health and continued her postdoctoral training at Harvard in molecular epidemiology. Welcome, Dr. Kile. You may go ahead and begin.
Thank you very much for that wonderful introduction, Diana, and welcome to everybody. We're going to start, so the title of the presentation is Exposure to Flame Retardant Chemicals and Social Behavioral Outcomes in Early Childhood. And if we go to the next slide, which is slide 2, I do want to declare a conflict of interest. Dr. Kim Anderson invented the silicone passive sampling wristbands that we used in this study. She received an NIH Small Business Innovation Research and Small Business Technology Transfer grant to commercialize this technology. And this all happened as we were doing this study. She subsequently has formed a company called MyExposome, which is dedicated to creating an awareness and a market for passive environmental monitors, such as the silicone passive wristband sampler that you're going to hear about in this talk. And because of this, she may financially benefit from the outcomes of this research. So if you're interested in this technology, you can either contact Dr. Anderson directly, or you can learn more about it through her company, which is MyExposome. We managed this conflict of interest by developing an analytical plan that had Dr. Anderson focus strictly on the environmental chemistry. So she developed the analytical method for measuring 41 different flame retardants, and she analyzed the samples for the wristband data. However, we had her blinded to all aspects of the data collection and the study design, and she did not participate in any of the data analysis. With that, none of the other investigators on this study have any conflict of interest. So slide 3 is kind of a background of the talk that I want to give today. I want to discuss the background of sampling flame retardants. I want to introduce the study design that we used in this pilot project. I will be presenting data that shows the flame retardant exposures that we measured in Oregon preschool-aged children. And then I'll go into the results of the analysis that show associations between the flame retardant exposures and the social behavior scales, as well as the strengths and the limitations of this study. Next slide. So we're on slide 4. As a background on flame retardants, which I am sure this audience is very familiar with, there are kind of 2 major classes of flame retardants. There's the polybrominated diphenyl ethers, or the BDEs, and the organophosphate-based flame retardants, the OPFRs. These are both found in a lot of different consumer products, primarily polyurethane foam, building materials, electronics. The PBDEs have largely been discontinued in use in the United States starting around 2005, and they were replaced by the organophosphate flame retardants. That was done in order to maintain flammability standards that were started as a state regulation. Those regulations, fortunately, have recently changed, and flame retardants are no longer required to be in consumer products. That being said, it doesn't mean that they're not there. There are concerns about exposure to flame retardants and how they may contribute to adverse health outcomes. In particular, there's been concerns about children's neurodevelopmental health. Exposure to these compounds are typically measured in either the blood or in house dust, indoor air, or hand wipes. And anybody who has followed this line of research knows that Heather Stapleton has really led the charge on a lot of these different measurements. The challenge with those is they're either proxies, i.e. the amount of the flame retardant in the house dust, and then you have to extrapolate to exposure to the child based on how much time they have spent in each of those microenvironments, or it's kind of invasive with a blood draw. We do know all of those methods are used in epidemiological studies. They all have strengths and weaknesses. So that kind of led into the development of the silicone passive sampling device and testing it for flame retardants. So next slide, slide 5. Kim Anderson's lab, she invented a silicone passive sampling technology that's based around a wristband. These are actually the same kind of devices that you've probably seen in social media campaigns like Livestrong or Cancer Awareness. It's that very flexible silicone rubber. What Dr. Anderson figured out was that you could extract any of the background contamination that is just present in that silicone due to the manufacturing process. And then once they have been cleaned, they basically act as passive samplers. They will absorb any lipophilic organic compounds. They passively diffuse into the silicone. When you analyze the wristband, they provide a time-weighted average exposure. So however long the wristband is worn is your metric, your duration that you use for the time-weighted average. You can actually wear this in any conditions and it will continue to sample. So you can wear it in water, you can touch the soil. They're kind of very easy to use in that respect. They reflect dermal and inhalation pathways. We do know they do reflect dermal pathways because Kim has been able to detect metabolites of cigarette smoke, so cotinine, as well as metabolites of caffeine, and the only way that could happen is if the device was picking up compounds that were in the skin of the wearer. They're also kind of practical. They can be transported at room temperature. You can wrap them up into a Teflon bag, seal them, post them in the mail. So they do cut down on a lot of logistical challenges that happen with the field and field sampling. She's currently tested and been able to qualitatively analyze 1,527 different analytes. And she's made all of this available freely on her website. So that's the link at the bottom of the page, which is the Food Safety Environmental Lab at OregonState.edu. So if you're interested in what chemicals have been measured, she's also posted the methods, and you can find out all of that information. So she's made most of this, actually all of it, pretty much publicly available. What we didn't know at the time is adults were able to wear these samplers, but would children? So that was one of the questions that we had moving in. I think anybody who's had a small child recognizes the challenges of even keeping their socks on, let alone a sampler. So next slide, slide 6. So with this, we started a new collaboration here at Oregon State that involved Kim's group, so analytical chemists, me, I'm an environmental molecular epidemiologist, as well as early childhood health specialists, so So that's Megan McClellan, Megan McDonald, and Shannon Lipscomb. So we started a cross-sectional study design. We recruited 92 children between October 2012 and January 2013. We focused specifically on preschool-aged children in 2 Oregon communities. So they're aged 3 to 5, but we were recruiting them as they entered preschool for the first time. We visited the home of the participants where we collected house dust, hand wipes, and we asked the child to wear the wristband for 7 days. Parents completed socio-demographic questionnaires that collected a lot of information about covariates. We asked the preschool teacher who had 1 or more of these children in their class to complete a social skills improvement system rating scale. This is a standardized assessment that is commonly used in children's early learning environment and assessments. It measures the children's social behaviors in a classroom setting. So that SSIS scale has 7 subscales. They measure communication domain, cooperation domain, assertion, responsibility, empathy, engagement, self-control, externalizing behavior, bullying, hyperactivity, inattention, and internalizing behavior. Now I'm going to point out that this is a lot of comparisons for a very small study design. So we a priori collapsed the 3 subscales of externalizing behavior problems, so externalizing hyperactivity, inattention, and bullying, into an aggregated outcome to try to reduce the number of scales that we were assessing. We did that because oftentimes these are very highly correlated, and so we just made that decision up front. Next slide, slide 7. We also did some other components with the covariate questionnaire data that we collected. So we did control for a family context. Again, because this was a small sample size, we collapsed a lot of information on maternal education, parental education, maternal employment, parental employment, house income, and home learning environment into basically a nominal score, which we controlled for in the analysis. Because I was working with people who have specialization in early childhood and have a lot of experience assessing social experience, and we know that the social environment often interacts with the chemical environment, we also collected information on adverse social experiences experienced by the child since birth. We asked the caregiver to answer 4 questions, which we turned into a score. Whether the child has ever lived with an adult with a substance abuse problem, whether that's alcohol or drugs, whether the child has lived with an adult with a mental health issue, which could be depression, suicidal tendencies, or a more severe form of the mental health issue. We also asked if the child had ever experienced violence, trauma, or neglect, or if they had ever witnessed domestic violence. And we took that information and we created an aggregated score of, that basically gave a child a range of 0 to 4. Next slide, slide 8. I do want to comment about the ethics of our study. So all research activities were approved by Oregon State University's IRB board. All parents gave informed written consent, and we did ask children to give their assent verbally before partaking in any research activity. Children were basically given 2 different opportunities to not consent to wear the wristband or participate in some of the assessments. We did return the results of the chemical analysis from the wristbands to the parents. Because this is kind of an unusual assessment technology, we basically reported back the results to parents in a way that let the parent know where their child's exposure level was relative to the rest of the population that wore the wristband. So we basically said your child's wristband was either in the top highest 25 percentile the lowest 25 percentile, or kind of at the average level across the 41 different compounds that we measured. Parents seemed to appreciate those results, and actually we didn't really get many questions about it. We did give all parents resources created by the Agency for Toxic Substance and Disease Registry so that they could learn more about the chemicals that we were measuring. And the Oregon Environmental Council has a really nice little handbook that's an EcoHealth Homes Checkup Kit, which kind of works through different interventions that people can take in their home to reduce their exposure, if they wish, to some of these compounds, including flame retardants. So it was kind of a handy outreach activity that was already created and did cover flame retardant reduction activities. Next slide, so slide 9. This is our basic demographics in our study. So you can see that 64% of the children were male. The mothers were employed, 66% of the mothers were employed. 88% of the fathers were employed. On average, the children were 4 years of age, ranging between 3 and almost 6 years of age. You can see that within the context, the different covariates that we measured and included in that family context score, education, both maternal and father's education, and also that household income, the higher that number on a range of 1 to 8, the higher the socioeconomic status. What we ended up capturing was actually quite a high socioeconomic group of children, which likely reflects the fact that this was a convenient sample done in the communities that surround the 2 Oregon State University campuses. So this is not necessarily a generalizable population with regards to education or income. Next slide, slide 10. Here is the range of scores that you can see for the different domains captured by the SSIS score. And what I kind of wanted to just point out here was you can look at the min to the max on the edge of the columns. And you can see that we did have a range of responses. Overall, it was quite a narrow range, but there was variability in the outcome measures that we were using. So next slide, slide 11. I wanted to present some data just on the exposure assessment. So of the 92 wristbands that we distributed to the children, we were able to get 77 returned for analysis. So we basically, when we went to the home to collect the other sampling, we gave them the wristband. We helped the child put it on. We explained the information to both the parent and the child about what the wristband was doing, that they could wear it either as on their wrist, and as you can see from this photo, even though this was the smallest size, preschoolers are tiny, and so many of them actually ended up opting to wear it as an anklet instead because it was a little tighter. They could wear it. We wanted them to wear it all day and all night. That being said, if the child did not want to wear it at night, we just asked them to put the wristband on the nightstand or somewhere next to the child while the child was sleeping. We had the parents return the wristbands to the lab via mail, and so we got that about an 84% response rate, which for those of you who have done this type of field sampling is actually really pretty good. When we analyzed the chain of custody information that asked to see, did the child wear the wristband, was it left in a car, any unusual activity that happened to the wristband, we did find 5 samples that were not really worn to protocol. So, one went through a washer and dryer, one ended up buried in a sandbox for a while, and then one got locked in a car. and found after the fact. So there was very good reasons to think that the data collected in those 5 was not representative of what the actual child would be, so we excluded them. So there's a 6.5% exclusion. So our overall sample size for the wristbands was 72. The extraction method, if you're interested in the chemistry, is described by O'Connell et al. In Environmental Science and Technology, which was published in 2014. Kim's group did develop a GCMS method to analyze 41 different flame retardant analytes. That included brominated, some phthalates, as well as some organophosphate compounds. It's I think it's actually one of the more comprehensive analytical methods that's out there. It did have quite good surrogate recovery. We spiked the samples with 2 different flame retardants with 2 different molecular weights, and you can see that the recovery was between, it was about 73% plus or minus 32%, and as good as 93% plus or minus 29%. The limit of quantification was quite low, so these you can actually extract or detect at quite a low level. What you're going to see there, though, is the unit of measurement is nanograms of chemical compound per gram of wristband. So it's not necessarily an air concentration. It's not necessarily a dermal load. And that does make comparing the results that we've measured in these wristbands, it's difficult to compare them to other study designs that have measured flame retardant exposures in different metrics. So that's kind of a challenge at the moment. How high and how low and how do our study compare to others is a challenge that we haven't quite cracked yet. Next slide, so slide 12. What you see here in this figure is the most abundant flame retardants that we detected in the wristband. So these are the 11 compounds that were detected at 60% or more of the wristbands. So the most frequently detected compounds. You can see that they're ranked, ordered by the concentration detection. So TDCIPP, which is one of the organophosphate, and TPHP is another organophosphate, TCIPP, another organophosphate, and TCEP, which is the 4th organophosphate that we measured. Those were all some of the most abundant flame retardants measured in the wristband. And what's worth pointing out is, again, these are the replacement compounds for the brominated diphenyl ethers. So these came into the market, well, we think they kind of came into the market after the BDEs are being phased out. So this puts them kind of in the mid to early 2000s. You can also see that we were still able to detect several brominated diphenyl ethers, the most common being BDE 47 and 99, and compounds that are still lingering in the indoor environment, probably from reservoirs in furniture. Next slide, so slide 13. We did look to see whether there was anything that was associated with the total levels of the different classes of flame retardants, and we did this using multivariate linear regression models. So what I ended up doing was I collapsed the organophosphate flame retardants into a sum total score, and I collapsed the BDE individual congeners into a sum total score. So basically what the outcome is there that you're seeing is what factors are related to all OPFR exposure and what factors are related to all BDE exposures. Vacuum frequency, home age, and family context were all related bivariately to OPFR exposure. In adjusted models, though, only home age and family context. So homes that were built after 2005 had higher levels of OPFR, and families that had a higher context score, so that's the education, socio-demographic variables, everything that was combined, had a lower OPFR score, and those factors stayed significant after adjustment. With BDE, again with a bivariate score, vacuuming frequency, home age, and family context were all related, but upon adjustment, only home age stayed significant for BDEs. So again, those homes that were built, in this case it was before 2005, had the higher level exposure. So what you're seeing there is actually the way I presented it on the slide is homes built after 2005 have lower BDE exposure, and that's really because they have higher OPFR exposures. So you do kind of see a shift in the chemical environment in the indoor arena with regards to these two different classes of flame retardants around the time that the U.S. Started to ban or manufacturers withdrew brominated diphenyl ethers from the market. Next slide, so slide 14. This is the results of associations between the flame retardant exposures and the different social scales measured by the preschool teachers. So this is a multi-regression analysis that examined the relationship between the two classes of flame retardants and social behavioral subscales. We did have to reduce the sample size now down to 69 because of some missing covariates, but these are adjusted for gender, age, family context, and the child's exposures to adverse experiences. What I'm presenting are the three subscales that showed an association with these chemical compounds. So what we really saw was relationships between assertion with brominated diphenyl ethers, where you saw less assertive behavior in children that had higher BDE exposures. With regards to responsibility, we now see the association with organophosphate-based flame retardants and a weak association with the BDEs, but we see that those children that had the higher OPFR exposures had a significant decrease in responsibility behaviors observed by the preschool teacher. We also see an association between OPFRs and externalizing behavior, where there is an increase in externalizing behavior, and I think there's actually a typo. No, there's not. So the p-values, the significance of the association is reflected by the asterisk. So these are kind of grouped, and I will show you the shapes of the dose response in the next couple slides. What I think is interesting to point out as well is the R squared. So this is the amount of variability explained by the flame retardants as well as those covariates, so gender, age, family context, and adverse experience. The R squared with all of those covariates in the model explain between 35 and 44% of the variability in these behavioral domains, which is pretty good. Like that's a well-fit model. What we did too was we looked at the R squared if we took the flame retardant variables out of the model. So this is only if we controlled for gender, age, family context, and adverse social experiences. What you can see is that the amount of variability explained in the model decreases substantially to 19% up to 29%. So flame retardants are explaining a good proportion of the variability. What I also want to point out is if you look at that adverse experience. So again, remember this is a sum score of the children who experienced one or more of those four adverse social experiences: living with a parent with substance abuse, living with a parent with a mental health issue, experiencing violence, trauma, or neglect, and also, and I'm just blanked on the fourth one. What I want to point out is the size of the beta. So these are standardized scores. So we standardized all of this so that you can compare the size of the effect across the different covariates. If you just look at externalizing behavior, you can see that children who experience the most adverse social experiences, that it's about 0.31. When you look at the same beta for OPFRs, it's 0.24. So it's not quite as large of effect as known adverse social experiences, but this is still quite a high beta. So this is why we're kind of saying that, well, this preliminary data anyway is showing that the effect of OPFRs may be on par with adverse social experiences in the child. And that to us is worth further exploration. Next slide, slide 15. So these are graphs now. So we also, not only did we do the analysis using the multivariate linear regression, which assumes linearity in response, we also looked to see the shape of the dose response curve using generalized additive models. So this allows the, well, it's a nice way to kind of graph out the data and see, well, what does the dose response look like? So this is on the panel A, which is the left side of your screen, is the dose response relationship, or exposure response, I should say, between OPFRs and externalizing behavior. And then the panel on the right, panel B, is the exposure response relationship between BDEs and externalizing behaviors. So what you can see from the A panel, the OPFRs, is actually that the exposure response is fairly linear. So what those little hash marks are on the x-axis are individual exposures. So you can see that we did capture a wide range of exposures, and that overall, that's a pretty straight line. When we looked at BDEs, you really don't see anything. That line, while there does seem to be a sharp increase at the low dose exposures, there really isn't a consistent shape. So in the nonlinear models, OPFRs were also related to that externalizing behavior. So this was kind of a sensitivity analysis to look and see whether the assumptions of linearity held. And in the case of OPFRs and externalizing behaviors, that seems to be the case. Next slide, slide 16. This is the relationship between the flame retardant classes and responsibility behavior subscales. So here again, OPFRs are on the left, BDEs are on the right. You can see that as OPFR exposure increases, you do see a general kind of nonlinear, but more or less decreasing response with responsibility. This also supports, or it's consistent anyway, with the multivariate linear regression, even though this line is not nearly as straight as the externalizing. It does seem to hold that, although there might be a threshold where it's really only those children that have the higher exposure experience that decline in responsibility behavior. Again, you don't really see much on the BDE scale in the sense that, well, maybe there's a effect at the low levels that tapers off, but that model did not show a significant relationship. Next slide, slide 17. Same kind of exposure responses. This is for the assertion subscales. Here you can see that the OPFRs really don't have much of a relationship, whereas in this case the BDEs, the higher the BDE level, that's a fairly linear decrease, although again there might be a threshold at the higher levels. Next slide. So as I kind of mentioned at the beginning of this talk, this is very much was a preliminary pilot study test. We were trying to see whether or not the children would wear the wristbands. We were trying to see if we could detect flame retardant chemicals in the wristbands in the children's environment, having worn them for just 7 days, and also whether or not there was any association with behaviors. So there's a lot of strengths and limitations with this, and I would very much call this a preliminary pilot study that needs further exploration. The strengths are that the measured personal exposures that we did with the wristband, the advantage of it was really that it captures the children's exposure to these compounds in every microenvironment encountered by the child. The child's wearing it. So this, if you can think about, even though children spend most of their time in their home, they also spend a lot of their time, in the back seat of a car, strapped into a car seat. They're spending time in preschool environments, and this sampler is measuring their exposures in each of those environments. So it really is capturing the child's average time-weighted exposure to these compounds. The wristband, even though it does measure dermal exposure, we're kind of thinking that it's mostly the inhalable fraction of these compounds, which has been an understudied route of exposure. The other strength of our study was we were able to control for a lot of potential confounders and effect modifiers, specifically negative social experience, which is not always captured in a lot of chemical epidemiology studies. And also these outcomes were rated by the preschool teacher as the child entered the school for the first time. So the teacher's blinded to the children's home environment. The teacher's blinded really to any previous behavior that, and they haven't seen this child before. So there's no carryover from, a bad experience in a class the year before that might taint their assessment of the child. So those were all strengths of this study. The limitations, though, are noteworthy. This was a cross-sectional study design. We only measured exposure for 7 days. We're not sure how that might change over time. It is a small sample size. Again, because of our recruitment convenient sampling, really the underlying population is very well educated and has a high socioeconomic status. So we're not sure these results would be generalizable to a broader population. We also, because of the wristband sampling, we're really not getting any measure of the children's ingestion of flame retardants, and we do know that house dust is a major route of exposure. So we're probably underestimating the child's total exposure to flame retardants. And also there is an ability to infuse the wristband with performance reference compounds so you can calculate the concentration in the air. We opted not to do that for this study, partly because we weren't sure how the children would interact with the wristband, and if we were going to inject any compound into the wristband, we didn't want the child to be exposed to anything extra. So if they were to suck on the wristband or do any of that type of behavior, we were a little nervous about that. That did not seem to be the case, so we might do this in the future. But as it stands, we can't calculate a concentration in the environment surrounding the child. That's why I pointed out that the results for this is in nanograms per gram of wristband. Next slide. So overall, the conclusions that we drew from this preliminary study was that children in Oregon are exposed to flame retardants, and the most abundant compounds detected in the wristbands were the organophosphate-based flame retardants. So these are the newer ones in our environment. Those organic-based flame retardants, the OPFR exposures measured in the wristbands, likely reflects inhalation pathway and was associated with more externalizing behavior problems in the children and poorer personal responsibility after controlling for other major risk factors. We also saw that the brominated diphenyl exposures measured in the wristband, which again reflects the inhalation pathway, was associated with less assertive behavior after controlling for other risk factors. Finally, we have to acknowledge a lot of people in this study. Because this was a pilot study, we were able to get funding from the NIEHS-funded Environmental Health Science Center at Oregon State University. So we received a pilot grant from them, as well as from the Hallie Ford Center here at OSU. Because we didn't have a lot of funding for this, we really used a lot of students, and they were fantastic. So a lot of students did a lot of the legwork, visiting all the families in the homes and doing a lot of the data collection. We also need to thank our preschool teachers. They were fabulous in filling out their response. And if you're interested, this results that I just kind of presented are available in a paper that was published in Environmental Health, and that's the link on the bottom. It is an open access publication, and you're more, I encourage you to go look at it and mull these results over, see if you come to the same conclusions, and I'd be happy to answer any questions you might have. So thank you very much for your time.
Thank you so much, Molly, for sharing the results of this important study and exciting new technology to measure exposures. I know that there are some non-scientists on our call as well, so I just want to encourage people to ask questions about the study if anything was unclear. But we welcome questions from anyone who's on the call, and if you'd like to ask a question, please press *2 to unmute your line and state your name and affiliation. We have about 10 or almost 15 minutes actually for discussion, so welcome to everyone.
Hello, this is Kristen Kate, and I work for Zender Environmental Health and Research Group here in Anchorage, and I also work with the National Tribal Toxics Council, and flame retardants is something that's very much a concern for them, and something they're trying to help tribes across the country better understand. I am wondering when something like this opportunity or wristband technology might be available for tribes to possibly try out in their community.
Yeah, no, that's a great question. It's available in a couple different ways currently. So Kim's business is now up and running, so there is the possibility if you wanted to just order some wristbands and do the analyses yourself, you can go through myexposome.com. Also, what I don't think got mentioned is I'm the director of the Community Engagement Core at Oregon State University's Superfund Research Center. The focus of our core is really working with Native American populations, investigating the environmental health concerns that they have using resources that are available within our Superfund Center. So if you wanted to drop me a line, there might be a possibility of developing a proposal or a project to put into the Superfund Research Center. So that's one way to get involved. When we do that, there is a process that we go through. We make sure to be following best practices with tribal groups. Tribes own the data. We basically just facilitate the connections. So I'm happy to explore that further with you offline. And then if you're interested in just understanding and getting measurements on flame retardants that might be present in an indoor environment, I'm going to direct you to Heather Stapleton. So she's also part of a Superfund Research Center. And what they've done, which I think is just so fabulous, is they have kind of a crowdsourced opportunity where you can send them a plug of foam from your sofa and log it into it's Duke Superfund Research Center, Heather Stapleton, and they analyze about 50 samples a month for free, and they will tell you what flame retardants are present in the sofa that's in your home. So that is a completely free service that's currently available, and I think it's just a great way for people to learn whether or not these compounds are in their environment, because otherwise it's really hard. I'd also say that I've been in discussions with Pam Miller and other people at ACAT trying to figure out how we could possibly do a study like this up in Alaska. So there's a couple things that are afoot. I hope that helps answer your question somewhat.
Yeah, that's fantastic. Thank you. Yes,
You're welcome.
Thank you. Again, if you'd like to ask a question or make a comment, please press *2 to unmute your line. And once you're finished, if you could press *2 to mute your line again, that will help reduce any background noise.
Can you hear me?
Hello. Hello. This is Alex Madonic in Berkeley, California. Can you hear me?
Yes. And for the other person who was trying to ask a question, you'll be next, so please pipe in.
Thank you. I'm going to mute myself till then.
Okay, sounds good. Go ahead, Alex.
Right. So I'm a chemist. I've worked with Arlene Bloom and the Green Science Policy Institute in the past, doing some consulting with them. And I'm trying to sort through the alphabet soup here, the different compounds. I haven't had time to read your paper yet, but I saw the top phosphate flame retardant on there appeared to be PDCP, the dichloro trisphosphate, and then there was the monochloro, and then I also saw TCEP, which is kind of shocking, but that's been on the California Proposition 65 list forever. And if it's there at all, it's clearly an exposure that's not appropriate, and if it might be introduced, as a byproduct in making another flame retardant like V6, but PDCP is also now in the Proposition 55 list here. So, I mean, the exposure to either of these compounds is questionable from a legal point of view, and that's the highest scoring one of all. So I just wonder if you have anything to say about that.
Yeah, so if you want to see the actual levels and more information about what we detected, I am going to point you to that on slide 12 at the footnote. We published that data in Environmental Research in 2016, so you can find more details about what that is. With regards to finding those compounds in the environment, yes, I was surprised, I'll be honest. I do think, being the northern neighbor of California, I think some stuff gets shifted north because our state regulations are different. And one of the motivations for this study was, I've been very familiar with the work that you've done at Berkeley and also Amy Zoda's work out of UCSF. But I saw somewhere a very small study that was done by an environmental group in Oregon that showed that the BDE levels in Oregon women's breast milk was actually the highest in the nation. And so it makes me wonder if some of the products that are not desirable in California are being pushed into the neighboring states. And that's why we're seeing it at these levels. Also, you have to remember that there's a lot of reservoirs for these compounds in our environment. So they're there.
Right, but the trisphosphate exposures, went up with newer houses, right? So it's new stuff. Whereas the PDBEs, the brominated flame retardant exposures, go down with new houses, so they're phasing out. It's clear that the trisphosphate flame retardants are heavily used right now. I mean, they're in products that you buy right now.
Yeah, I think there's a lot of work that we still need to do on this issue.
I'd like to go ahead and invite the person who wanted to ask a question before to unmute her line.
Thank you. This is Kim Yolton. I'm calling from Cincinnati, and I have about half of my study team here in the room with me, too. This is really relevant. I read the paper when it came out, and so I was really excited to see this presentation. But it's very relevant to what we're doing. We're following a cohort of kids that we enrolled during pregnancy, or during gestation, I should say. And we are now seeing them at age 12, and we're using the SSIS as well, which I've not seen used in research before, so I'm excited that somebody else is using it too. And we are also looking at flame retardants and a gajillion other things. But I have a couple, just a quick question about if you could clarify and let me know if you did any sensitivity analyses to look at whether there was a difference by where the children wore the wristband, because I would think that there would be a difference in exposure based on wrist versus ankle, because the house dust is probably going to be a bigger exposure route than, and that would maybe allow greater exposure at the ankle location than the wrist. And then the second question was whether you looked at seasonality. I don't know how long your enrollment period was, but if in the summer months kids are spending less time indoors, they would potentially have reduced exposure during those time periods. So I just wondered those two things, whether you've looked at that. I know it's a small sample size and it's hard to break that down, but just a question about that.
Yeah, no, those are great questions. With regards to the seasonality, because that's the easier one to answer, this was all kind of measured in the fall term. So all the kids were back in school, and it was kind of October, November that we did the exposure component. So not quite winter yet, not quite summer. So it was standardized a little bit like that, and we have not looked across the season because, yeah, I think that would influence their overall patterns of exposure. Oregon is really wet during the winter, and while they're pretty brave people going out and about and doing their thing, it does shift behaviors and people spend more time indoors, whereas the summers here, I think everybody's outside as much as possible. So I think that's a really good point, and there probably is seasonal variation to exposure. With regards to the sensitivity of wearing it on the ankle versus the wrist, that is a good question. We did not look to see if there was a difference. These are passively diffusing, so yeah, you could make the case that maybe the ankle is picking up, you know, is in a diffusion layer that is slightly more concentrated than a wrist. You could probably assess for that. If it is truly in the vapor phase, I can share the antidote that Dr. Anderson likes to share, which is if you're in an elevator and somebody passes gas, everybody smells it. So it's the same principle of diffusion at work. So, you know, it'll take a little more time to get to, you know, maybe your ankle or your wrist or your nose in that metaphor, but it will eventually get there. So it probably does make a subtle difference, but whether that's a meaningful difference, I'm not sure.
Did you have like like what was the rate of ankle versus wrist that the parents, because obviously it's a parent's choice where they're going to put it probably.
Yeah, most of the kids wanted to wear it on their ankle.
Okay.
And I think it was just tighter and not as fidgety. Because you can kind of see from the photo that's on slide 11, you know, it kind of, with the littler kids, particularly, it worked better as an ankle. Because it was just, even though this was the small size, it can kind of slip down to the wrist. But it was fun. The kids actually got into it. A lot of them were calling them their science bracelets. Although apparently color matters more than we thought. Some people did not like beaver orange. So we now have them in, Kim now has them in different colors.
Thank you for your question. I think we have time probably for one or possibly two more. Again, *2 will unmute your line.
Hi, this is Patty, and I know your topic was very specific around social behaviors, but I am wondering if you perhaps might know, at the levels of exposure that you're seeing, are they in any way correlated with studies that have showed other kinds of health harms besides social behavior with the flame retardants?
Yeah, no, that's the million-dollar question. At this point in time, I can't answer that. The fact that these measured in nanograms per gram of wristband make it, we can't really extrapolate that beyond that value, that unit of measurement, to be able to compare this result to other studies that have been done. So I don't know.
Thank you.
I think actually the only way we'd be able to do that is looking at the house dust samples, because that seems to be a more common way to measure this. But how to take this to blood, like that's a really challenging question.
Do we have one more question out there?
Yeah, this is Priscilla Evans. I was just wondering, are those bracelets available out there somewhere, or would you find them?
Yeah, so if you want to just do a commercially available way to do it, that is where Kim has developed through small business innovation research grants from the NIEHS. She's developed a company called MyExposome, so you can find it online, myexposome.com, and that will take you into the commercial side of this business. She also does do a lot of research projects, and she's been involved with groups like the Environmental Defense Fund, so you could try contacting her and seeing if any of those kind of projects are going on. And I do know that other research groups have cottoned on to using the silicone wristband. So I think there's folks out at Duke University and maybe University of North Carolina. There's a few other groups now that have figured this out. And if you are a chemist or involved with a university, I'll point you to the resources, the link anyway, that's on the bottom of slide 5. That link, http://fses.oregonstate.edu/methods. Kim's made all of her analytical chemistry available online. So you can go there and learn how to do this yourself if you are attached to a laboratory or a university that has the right equipment to do this. So there's about 3 different ways, but it is still relatively new technology.
Thank you, Molly. And I think several things were mentioned that are resources for people to follow up with this. So I will be sending a follow-up email, which will include a recording of today's call, as well as links to some of these resources and opportunities. So we are out of time, and I just have a few closing announcements. I want to thank everyone for participating today, and to thank you, Dr. Kile, for your time in preparing this presentation and in presenting to us today. Our next Che Alaska call will be on Wednesday, May 24th. We will be discussing outcomes from the Conference of Parties to the Stockholm Convention, an international meeting taking place right now in Geneva, Switzerland. And the Stockholm Convention is a living treaty that recognizes the need to take global action on persistent organic pollutants. The treaty's expert scientific committee has recommended 3 substances for global elimination to be added to over a dozen others. Join this call to find out what was decided at the Conference of Parties and the implications for indigenous people in the Arctic. And our speakers will be Pamela Miller and Vai Wahihi of Alaska Community Action on Toxics, and Rochelle Diver of the International Indian Treaty Council, and they are all there in Geneva as we speak. Again, thanks to everyone for participating today. Please consider making a donation to Alaska Community Action on Toxics to support these monthly calls. Whatever you're able to contribute will be appreciated and will help provide the support we need to continue bringing you these calls with amazing researchers and policymakers each and every month. You can make your contribution online at www.akaction.org. And if you have any additional questions or comments, please feel free to contact us. The phone number for Alaska Community Action on Toxics is 907-222-7714. You can also email me at diana@akaction.org. And thanks again to everyone. Have a wonderful day.